Okay, let's talk about something you see every single day: water. It's everywhere, right? We kind of take it for granted. But what if I told you that this simple little molecule, H2O, is actually one of the biggest rule breakers, one of the strangest substances in the entire universe? Yeah, really. So let's dive in and uncover some of its secrets.
I mean, look at this. It's just a glass of water. Simple, right? It's the lifeblood of our planet. It covers most of the Earth's surface, and it makes up a huge chunk of our own bodies. It couldn't be more familiar. But here's the thing. That familiarity, it's hiding a completely rebellious nature. Water is constantly defying the laws of chemistry and physics as we know them. And the craziest part is, it's because of these quirks, these weird little rule breaks, that life on Earth is even possible. Pretty wild, huh? So here's what we're going to get into. We'll look at water's secret identity and the super strange anomaly of ice. Then we'll see its ultimate disappearing act as a solvent, figure out what happens when it hits its saturation point, and finally, how we can go from a solution all the way back to a crystal. Let's get started.
All right, first up, the anomaly of ice. This is probably one of water's most famous and most vital quirks. See, normally when things get colder, they shrink, right? They get denser. But water, nope. Water marches to the beat of its own drum.
So check out this graph. As you cool water down, it gets denser and denser, which is totally normal. But then it hits 4 degrees Celsius and something bizarre happens. It hits the brakes, turns around, and starts to expand. It actually gets less dense as it gets colder on its way to freezing. That is just not how things are supposed to work. And this one weird little fact has a massive impact on, well, everything. Because ice is less dense than water, it floats. This creates like an insulating blanket on top of lakes and ponds and oceans, and that layer protects all the life underneath. Just think about it for a second. If water behaved like everything else, ice would sink. Lakes would freeze solid from the bottom up. And, well, goodbye to almost all aquatic life. It's a total game changer. Okay, on to another one of water's superpowers. Its incredible ability to soak up heat. This number you see, 4.2 joules per gram per degree Celsius, is its specific heat capacity. And trust me, that number is exceptionally high. What it means is you have to pump a ton of energy into water just to raise its temperature by a tiny little bit. It's like a thermal sponge. So why does that matter to you and me? Well, for starters, it's the reason coastal towns have much milder weather than places inland. The ocean is basically a giant temperature regulator for the planet. It's also why we pour water into our car radiators. It's amazing at pulling all that dangerous heat away from the engine. And of course, it's how we maintain a stable body temperature. Water really is the ultimate thermal buffer. So water's physical properties are already pretty mind-blowing, but that's just the start. Its chemical behavior is just as fascinating. In fact, it's so good at dissolving things, it's earned this amazing title, the universal solvent. Let's see how it pulls off this ultimate disappearing act.
Okay, first, let's get our terms straight really quick. You take something like salt, that's our solute, and you dissolve it in something like water, that's our solvent. What you end up with is a solution, in this case, salt water. Easy enough, right? But the real question is, why is water so ridiculously good at this?
Well, the secret sauce is something called polarity. Basically, every single water molecule is like a tiny little magnet. It's got a positive end and a negative end. This high dielectric constant you see here just means it's really good at getting in between other charged particles. It reduces that force of attraction between them. So when you drop salt in, these tiny water magnets just swarm the salt ions, pulling the positive and negative bits apart until, boof, they've disappeared into the water. But even a superhero, like the universal solvent, has its limits, right? You can't just keep dumping salt into a glass of water forever and expect it to disappear. At some point, you reach a limit, and the water basically just says, nope, sorry, I'm full, no more room.
And that brings us to the idea of saturation. So think of it in 3 stages. First, you've got an unsaturated solution. There's still plenty of room, you can dissolve more stuff. Then you hit saturated. That's it, you're at max capacity for that specific temperature. But then there's this really cool kind of unstable state called supersaturated. This is where you trick the water into holding more solute than it's supposed to. It's a delicate balance, just waiting for the tiniest disturbance to release all that extra stuff. So how do we know where these limits are? Well, scientists have a handy tool for that. It's called a solubility curve. Think of it like a cheat sheet that shows you exactly how much of a substance you can dissolve at any given temperature. And you'll notice a clear trend here. For most solids, the hotter the water, the more stuff you can dissolve in it.
Yeah, let's actually pull a couple of examples right off that curve to see what I mean. Okay, so at a pretty warm 60 degrees Celsius, you can dissolve about 37 grams of good old table salt, sodium chloride, in 100 grams of water. But now look at potassium nitrate. At the exact same temperature, you can cram in a whopping 108 grams. So yeah, what you're trying to dissolve makes a massive difference. All right, so we've performed this amazing disappearing act, dissolving all the stuff into the water. But can we get it back? How do we reverse the magic? The answer is a really beautiful process called crystallization. And it's actually pretty straightforward. You take that hot, saturated solution we talked about, the one that's packed full of solute, and you just let it cool down. As it cools, the water can't hold on to as much stuff anymore. So what happens to the excess? It has nowhere to go, so it comes out of the solution and forms these amazing, pure, solid crystals. It's a really elegant way to purify a substance. But wait, it gets even cooler. Sometimes, as these crystals form, they actually trap little water molecules inside their structure. We call this water of crystallization. Take a look here. Those beautiful blue crystals on the left, that's hydrated copper sulfate. They have hidden water inside. But if you heat them up, that water escapes, and you're left with the white and hydrous powder you see on the right. And the best part? Add a few drops of water, and that brilliant blue color comes right back. It's like magic. And this whole idea of water being trapped in crystals leads to two final pretty neat phenomena. They're basically opposites. On one hand, you have efflorescence. This is when a hydrated crystal just spontaneously loses its water if the air around it is really dry. On the other hand, you have deliquescence. These are substances that are so thirsty for water, they'll literally pull moisture right out of the atmosphere and dissolve themselves in it. Two sides of the same coin. So there you have it. From ice that floats and saves entire ecosystems, to its incredible power to regulate our planet's climate, to being the ultimate solvent, water is anything but ordinary. It really makes you think, doesn't it? If a single, simple molecule that we see every day can hold this much complexity and this many secrets, what other wonders are just hidden in plain sight, all around us, just waiting for us to stop and take a closer look?